Okay, now that you've mastered series circuits, let's do part two, parallel circuits. Now, this is where it gets a little different, but a lot of the laws are very similar, yet kind of opposite, and you'll see what I mean momentarily. So just like in our series circuit, the first thing we always have to do is figure out what kind of circuit is it. Now, we knew the series circuit was a loop that did not have anything other than one circuit path. I described it as a single lane highway for electrons. Well, a parallel circuit has multiple paths. So let's look at this. Let's take our electrons from our battery and let's follow it. We got this one big loop here. So that's one path, but we also have a path that branches off here. And then we have a path that branches off here. So it's like coming up into a fork in the road, and you can take one road, another road, or another road. But in the end, they all meet back at the battery. So we have a path here, a path here, and a path here. So this is our parallel circuit. Now remember, we're using our DC cheat sheet as a reference with Ohm's law and our different formulas and rules and laws on it. So let's look at the formula for parallel circuits. Since we've identified this as a parallel circuit, this is where we're going to take reciprocals. So you're going to take the reciprocal of R1, the reciprocal of R2, the reciprocal of R3, and hit equals on your calculator. After that, you're going to take the reciprocal of that number. So let's do that together. So we're going to start with 560 ohms. So you're just going to put in your calculator 560. Then you're going to find the X -1 key. That's the reciprocal key. Some of your calculators might say 1/X, but most of them say X -1. So you're going to hit X -1. Then you're going to hit plus because you're going to add it to a 1,000 ohm resistor and hit the reciprocal button, the X -1 button again. And then you're going to hit plus 560 and hit X -1 again. You're now going to hit equals. You should end up with a decimal. You should end up with a small number. And then you're going to do the reciprocal of that, and it's going to give us an answer of 218.75 ohms. Now, one rule that you should be aware of, whenever you're solving a parallel circuit, your answer should always be less than the lowest resistance in the parallel. So even if this 1,000 ohm resistor was 1,000,000 ohms, my answer would still be less than 560. So whatever you look at a parallel, this could be 1,000,000 ohms, this could be 10 million ohms, and this could be 1 ohm. And our answer would be less than 1 ohm. These are pretty close in value, 560, 560, and 1,000. And sure enough, coming up with an answer with 218 sounds like a reasonable amount to be correct. But hey, let's hit our little correct button to be sure. And it tells us we're correct. How do we figure out I total? Well, cover up the I on your Ohm's law cheat sheet. And we know that it's E divided by R. So we're going to take our E, our V total, our voltage total of our battery, which is 17.2 volts. And we're going to divide that by our resistance of 218.75 ohms. And that's going to give me a total current of 78.628 milliamps. And let's check that as we go. And it tells us we're correct. Now, when we did the series loop, we said that current was constant in a series circuit. So IR 1, 2, and 3 were all going to be the same. Guess what? This is where it's the opposite. Remember I said you'll see what I mean? Some things are going to be opposite. And in a parallel circuit, voltage is constant. In a series circuit, the voltages were all different, adding up to I total. But think about it. If I took the plus and minus of a meter and put it here, and if I slid it around these wires, it would still be on the same wires. So my positive wire is up here across all three resistors, and the negative wire on my meter is down here across all three resistors. Actually, positives at the bottom, negatives at the top. Guess what? That voltage is going to be the same as the battery voltage, 17.2. So this is where you want to put in your 17.2 because Kirchhoff tells us the voltage across the parallel is constant. We put in 17.2 volts, and we're going to check that, and check that. Now, this is where we're going to solve our current. So current's going to flow through R1. Some current flows through R1, some current flows through R2, and some current flows through R3. All three of those currents should add up to our 70.628 milliamps of current. So the current in each resistor in the parallel should add up to I total. So let's figure out IR1. Cover up the I in your pi, and it's going to be E divided by R, or V divided by R. So we're simply going to take 17.2 volts, and we're going to divide it by 560 ohms, and that's going to give us an answer of 30.714 milliamps. Let's check that guy. IR2 is going to do, we're going to do the same exact thing. We're going to take the same 17.2 volts, but this time we're going to divide it by 1,000 ohms, which is going to be 17.2 milliamps. That's an easy one. You just move the decimal 3 places when you're going from the whole number to milli. And IR3 is actually going to be the same as IR1 because the value is the same. So 17.2 divided by 560 will also give me a current of 30.714 milliamps. Guess what? We said that I total was 78. 30 and 30 is 60, and 17 is 77, and then all this little remainder gets us up to 78 milliamps. If we add them up, that's what it adds up to, and that tells us we did our work correctly. We already know we got VR1, VR2, and VR3 correct. Power is the same for series and parallel. If I want to know power total, it's E total, our voltage of 17.2 volts, and we're going to multiply that by I total of 78.628 milliamps. That power is 1,352 milliwatts. PR1 is simply VR1 times IR1. So VR1, again, is 17.2 volts because Kirchhoff tells us that voltage across the parallel is constant. We're going to multiply it by the current through IR1, which is 30.714 milliamps. And that's going to give me a power of 528.280 milliwatts. Let's check that. The next one is PR2. PR2 would be VR2, again, 17.2 volts. We're going to multiply that by the current of 17.2 milliamps, and that's going to give me a power of 295.84 milliwatts. And then finally, we're going to do PR3, which is VR3 times IR3, 17.2 times 30.714 milliamps. Well, guess what? That's the same parameter as this one, so the answer should still be the same. 528.28. We'll correct that, and you can see we got all those right. Practice a few parallels before we move on to part number 3, complex circuits.